This is video number 21 in a series about complex arithmetic. We are now focusing on powers and roots of complex numbers, and we're also using Mathematica to make some animations to visualize what's going on. Quick review: if z is represented in polar form as r times e to the I theta, so that r is the modulus of z, which would be non-negative, and theta is an argument of z. And then if we pretend, let's say, n is a positive integer, then z to the n can be represented in polar form in this way. R to the n is the modulus of z to the n, and n times theta is an argument of z to the n power. We used Mathematica's Manipulate command to create an animation where we used Locator down here to allow us to change the animation by moving the cursor. Here's what it looked like. And we were looking at the fifth powers of this number. We looked at a wider view to see these points, but we can also now change this point to going in closer to the origin to see what happens. As you go around the horn here, that's the second, third, fourth, and fifth power of this number. When it's further away from the origin than 1 unit away, then the higher powers go even further away. When it's within 1 unit of the origin, then the higher powers go closer, and that should make sense to you based on the polar form. Let me go ahead and add the unit circle in here and show you how to do that. Within the show, I can add graphics and the command circle to create a circle. And if I just put 0, 0 inside here as sort of a default option for circle, that's going to create the unit circle, in other words, the circle of radius 1 centered at the origin in this picture. So we can see just when this change happens with the powers going further away versus going closer. And let's emphasize this even more by starting the point on the unit circle. Instead of 1 comma square root of 3, I'm going to start at 1/2 comma square root of 3 over 2. In other words, this is going to be the complex number 1/2 plus square root of 3 over 2 times I. And you can see all the powers are staying on the unit circle there. Let me also do something else kind of interesting. Let's add another animation parameter here that's going to look at even higher powers of this complex number. In general, let's call it the mth power. So I'm changing the 5s here to m's. So m is going to be an animation parameter. It's going to start at 1 and go up to, let's say, 50. Now if I just leave it like this, that won't quite do what I want, because unlike table, where the thing that's changing is assumed to go up by integer values, within Manipulate that doesn't happen. Manipulate assumes, if I just do this, that m is going to be a continuous variable going from 1 to 50. To make it go up by integer values, I need to add an extra comma 1 here. And that gives me a slider. You can see that I can open up and increment up by 1 or let it run to see the higher and higher powers. Let's step forward by 1 each time. There's the second power, third power, fourth power, fifth power, sixth power. Interesting, it looks like the sixth power is equal to 1. Seventh power, that looks like it's back where we started. And yes, we aren't getting anything new as we go past the sixth power. Is that really true, or is that just something that seems true based on how we're looking at it? Well, let's check it with ComplexExpand. Let's raise this number, for example, to the sixth power. And see if we do get 1. We do. Raise it to the seventh power. We do get the number itself back. So this is continuing to go around and around the circle in kind of a periodic way, you could say, coming back to where it starts. Does that always happen if the number starts in the unit circle? The answer is no. If I change this to start at another point on the unit circle, that is not, well, the ratio of this number with 2 pi will not be a whole number, not be a rational number. The ratio of its angle, I should say. If I pick 3/5, 4/5, think of it as the complex number 3/5 plus 4/5 I, it's on the unit circle, but again, the angle it makes with the positive real axis, if you divide that by 2 pi, you do not get a rational number. And because of that, something different happens. We look at second power, third power, fourth, fifth, sixth is not 1 for sure, and seventh is not back to where we started. Eighth is not even back to where we started, and in fact, turns out you can prove if you continue this, you're going to never ever get back to where you started. The higher and higher powers just keep being different numbers on the unit circle. So that's an interesting dichotomy to think about. This is all related to roots of a complex number as well. And let's go ahead and think about the complex number z equals 1 to start with, and wonder what are the square roots of 1 to start off with. Turns out you want to write in complex analysis, it's standard to write roots in terms of fractional powers rather than square root symbols, and the reason for that I'll tell you here in a minute. So, well, another perspective that you want to have with this is when you see this symbol, 1 raised to the 1/2 power, you don't want to just think square root of 1, you want to think all possible square roots of 1. All possible numbers whose square is 1. Let's call one possible number Zeta. Kind of a cool Greek letter there. To get it, I did escape, Z escape. It makes it Zeta. And let's write Zeta in polar form. And let's write its polar form as, well, rho e to the I times phi. Now what would have to be true for Zeta to be a square root of 1? And you might be thinking, well, couldn't Zeta just be 1 and negative 1? Well, let's see if that's what happens. If we square Zeta, what's going to happen to its polar form? You're going to get the modulus squared, and you're going to get the argument doubled. And we want that to equal 1. 1 can be written in polar form as 1 times e to the I times 0. It can also be written as 1 times e to the I times 2 pi. It can also be written as 1 times e to the I times 4 pi, etc. There are infinitely many ways to represent a complex number in polar coordinates, in polar form. But let's think about this. Rho does have to be a real number, and when I square it, it's got to be a positive real number, a non-negative one. Rho can't be negative. And in order for this to all work, rho squared is going to have to equal 1, and rho again is a real number greater than or equal to 0. Rho would have to equal 1. What about phi? Well, whatever we choose for phi, 2 phi has got to be either 0 or 2 pi or 4 pi or 6 pi or negative 2 pi or negative 4 pi. It's got to be a multiple of 2 pi, so phi itself has got to be a multiple of pi. Think about that. If phi is a multiple of pi, think about the polar representation of complex numbers. That means the only possibilities for zeta here are plus or minus 1, because in polar form 1 has an argument that's a multiple of 2 pi, and negative 1 has an argument that's pi plus a multiple of 2 pi, like 3 pi or 5 pi or 7 pi. So the only possible answers are plus or minus 1 here, and I guess that's comforting. But you might wonder now, what about cube roots? What about cube roots? Let's go through this whole analysis again, thinking about cube roots. And I guess I'm not going to get to explaining in this video why we use this notation here exclusively for roots. I change these 2's to 3's. What's going to happen? Well, once again, rho is going to have to equal 1. So the modulus of the roots has to equal 1. What about their arguments? 3 theta is going to have to equal 0 or 2 pi or 4 pi or 6 pi, etc. It's going to have to be a multiple of 2 pi. Meaning, for example, phi equals 0 works. Phi equals 2 pi over 3 also works, since 3 theta can equal 2 pi to make it work. Phi equals 2 pi over 3 will work. Phi equals 4 pi over 3 will work, 6 pi over 3 will work, 8 pi over 3 will work, negative 2 pi over 3 will work. And if you think about the complex planing, you think about the polar form, there's only 3 things that can be. Plus 1 works, e to the I times 2 pi over 3 works, e to the I times 4 pi over 3 works, and anything else you consider, like 6 pi over 3, 8 pi over 3, 10 pi over 3, is going to generate one of these 3 numbers. So these are the answers for the cube root of 3. And I want to be read there. If you think about what those are in rectangular form, 2 pi over 3 is 120 degrees. In rectangular form, it's going to be negative 1/2 plus I times square root of 3 over 2. If I expand this, complex expand here to the 3rd power, that should give me 1, and it does. And with the 4 pi over 3, it's going to be the same, except it's going to be the complex conjugate of that last number, and its cube is 1 as well. So we've just found the cube roots of 1. We'll consider another example in the next video.